So this episode, we're going to be continuing on with our challenge of building a high-speed defensive CLI log parser. With today's key theory concepts that we're going to learn is how to harden pattern extraction and regex primitives. So the mission briefing for this challenge is today's objective is to build a production-grade Python extraction utility that passes dirty configuration dumps and returns structured, validated network primitives. The core challenge is that you're building a utility that extracts 3 distinct types of network primitives from messy data. This includes IP addresses, both IPv4 and IPv6, and MAC addresses, as well as nested VLAN tags. To crush the day 3 objectives and ensure the logs don't bring down your production engineering workstations, you need to master 4 core pillars of regular expression theory. So what is regular expression theory? At its core, regular expression, regex, is a search pattern written in specialized syntax. Think of it as a highly advanced programmable version of Control plus F. Instead of searching for an exact fixed word like admin, regex lets you search for a type or shape of data, like a word starting with a capital letter followed by 4 numbers ending with an IP address. Here is the entire anatomy of regex condensed into 4 elements. So we have the core primitives. So -d matches any single digit 0 to 9. \w matches any single alphanumeric character, letters, numbers, underscores. \s matches any whitespace, spaces, tabs, and new lines. And the period equals the wildcard, matches any character except a new one. We also have quantifiers, which signifies how many times. So we have the star sign, which equals to 0 or more times. The plus sign, which equals to 1 or more times. 3 in curly brackets is exactly 3 times. 1, 3 in curly brackets is between 1 and 3 times. We have anchors and boundaries. So the up arrow symbol is the absolute start of the line. The $sign is the absolute end of the line. \b is a word boundary, for example, separating a number from a space. And custom sets and groups, so A to Z, a character class matches any single uppercase letter. We have the up arrow symbol 0 to 9, a negated set matches anything that is not a number. And the 3 periods in a row equals to a capturing group, isolates a specific piece of the match to extract your code later. So a quick example, if you look at this pattern designed to find a standard VLAN interface ID like VLAN 104, we write it as VLAN \d and 1 to 4 in curly brackets. So VLAN matches the literal letters VLAN, \d in 1 to 4 in curly brackets matches any number that is between 1 and 4 digits. In security automation, regex is the tool used to turn messy human-readable terminal output into neat machine-readable variables. So now that's out of the way, we're going to look at pillar 1, which is backtracking mechanics and redos, the security aspect. So Python's RE module uses a non-deterministic finite automation engine. This engine matches characters by trying a path, and if it fails, it moves backwards to try alternative path. This process is called backtracking. If your nest quantifies incorrectly, the number of paths the engine has to evaluate grows exponentially. An attacker can feed a carefully broken string into your parser, causing the CPU to spike to 100% indefinitely. This is known as regular expression denial of service attack. For example, we have the evil pattern example. So this up arrow a plus in brackets with the plus and $sign running against this sequence, the engine will try every single mathematical permutation of grouping those as A's before realizing it fails at the exclamation point. With only 30 characters, it can take billions of calculations, freezing your application. The fix is to avoid nesting quantifiers like the $sign and the A+. Be highly specific. Instead of this, you use bounded character sets, match anything that isn't a closing bracket. Pillar 2 is greedy versus lazy quantifiers, the extraction control. So by default, regex quantifiers are greedy. They want to consume as much of the string as physically possible. So the first pattern is greedy and can scans to the absolute end of the line, then backtracks 1 character at a time until it finds a match. The other pattern is lazy, scans character by character, stopping the exact millisecond it hits the minimum requirement to satisfy the match. Why this matters for netting logs? Imagine passing this log line. Greedy will match VLAN 100 interface gigabit 0/1 zone DMZ. It will look everything from the first to the final square brackets. Whereas lazy will correctly yield 2 separate matches, VLAN 100 and zone DMZ. Pillar 3, capturing versus non-capturing groups, memory optimization. When you put parentheses around a pattern, like \d 1 to 4 in curly brackets, you are doing 2 things simultaneously, grouping the logic and telling Python to save that matched text in memory as a separate object. The overhead problem, when you're streaming multi-gigabit firewall logs, capturing groups adds massive memory overhead because Python has to allocate RAM to hold every single group object it encounters. The solution is non-capturing groups. So if you need to group logic together, for example, matching the repetition of an octet block in an IP, you don't actually need to pull that single segment out later. Use a non-capturing group by adding the question mark and colon sign at the end of the parentheses. So the first example is bad. It allocates memory tracking tracking every single dot segment. But this new non-capturing group is excellent because it groups the logic cleanly without allocating extra memory tokens. The final pillar is the exact structural validation versus loose matching. A standard developer writes a regex to match text that looks right. A security engineer writes a regex to exclude text that is wrong. And now moving on to character classes over alternations, instead of using the logical OR operator for individual characters like A or B or C, always use character class. The regex engine processes character classes as direct lookup table, which executes significantly faster than evaluating multiple alternations. It is ETH or gig or 10. Fast explicit class is this for tracking clean hex bytes in MAX and IPv6 without checking every variation independently. The term 0-9A-5-FA-F is called a character class. It acts like a fast single character checklist for the computer. When the regex engine encounters this, it means match exactly one character as long as it is a number from 0 to 9, a lowercase letter from A to F, or an uppercase letter from capital A to F. These are the exact characters used to write hexadecimal numbers, which are the building blocks of MAC addresses and IPv6 addresses. The problem with the slow way: when the computer evaluates a slow way, it behaves like a clumsy inspector checking a list one by one. If it encounters the letter F, it asks, is it 0? No. Is it 1? No. Is it 2? No. It has to evaluate up to 22 separate conditions just to match that single letter across a multi-gigabit log file. This grinding process destroys performance. The speed of the fast way is that under the hood, the regex engine treats a character class as a direct lookup table or a bit mask. Instead of checking 22 individual options sequentially, the engine converts this range into a tiny mathematical boundary in memory. When a character arrives, the engine performs an instantaneous single-step check. Does this character's internal computer code fall inside our allowed hex boundaries? It's immediate yes or no answer. So when I was writing this, the question that I automatically thought of, which I'm not sure if you guys came up with as well, was how does this pinpoint Ethernet gigabit, for example? But the key point is that you must use this pillar in conjunction with other pillars to actually pinpoint the interfaces. A character class, like this one, for example, by itself only knows how to look for raw hex numbers. It has absolutely no idea what an Ethernet or gigabit interface is. To isolate a specific interface, you combine pillar 4, structural validation, with pillar 2, greedy versus lazy control, and pillar 3, capturing groups. Now we're going to move on to the pseudocode. I want you to take a moment to try and write this yourself. And in exactly 3 seconds, I'm going to cut this box and show you. So this is the exact pseudocode that you can use to write your final code. So for each line in the dirty log file, if an IPv4 address is found, add it to the IP list. If an IPv6 address is found, add it to the IP list. If a MAC address is found, add it to the MAC list. If a subinterface looks like name.outervlan.innervlan, extract outer VLAN, extract inner VLAN, add them to the VLAN list, print the final clean list. In Python, we import RE, brings in the built-in regular expressions regex engine. So by default, Python only knows how to look for exact matching text like text.find. When you import RE, you unlock a whole library of special pattern matching functions. It allows Python to understand concepts like find a number between 1 and 4 digits long, or verify this string fits the exact structure of an IP address. So I'm going to keep this in mind, so when you guys have a crack at the final code, you definitely want to import RE. So I'm going to cut the box in 3, 2, 1. And this is the final code for this challenge. So we start by importing RE. We have the dirty logs that we're going to use. And this is how you would compile the regex patterns using the rules that we covered before, such as the anchors and boundaries, as well as primitives, quantifiers. We then move on to storage containers. So for inline and dirty logs, IPv4 match equals to this .search line. And what you do is, if there is an IPv4 match, you have found _IPS.append match to group 0. So it will add an index and add this to the array. Same for 6, same for the MAC address. For VLAN match equals to VLAN underscore pattern search line. If VLAN underscore match outer equals to VLAN underscore match group 1, inner is VLAN underscore match group 2. Found VLAN do append this to outer and inner, pretty simple. And then at the end, it will print out the results. So a question that you guys might have is, why is it number 1 and 2 here? And it was 0 before. So number 1 indicates the first pair of parentheses the regex engine encounters when reading the pattern from left to right. Look closely at how we define the VLAN pattern. So this is the VLAN pattern equals to re.compile. Then we have parentheses 1 and parentheses 2. So if you go up here, you would see that this is the outer VLAN and this is the inner VLAN. When you wrap a part of your regex in parentheses, you are creating a capturing group. Python keeps track of these groups in sequential order. Group 0 is a special group. It always returns the entire text that matches the whole pattern. In this case, .105.301. Hope that makes a bit of sense. Group 1 extracts only the text wrapped inside the first set of parentheses, 105, because it comes first structurally. It represents the outer VLAN. Group 2 extracts only the text trapped inside the second set of parentheses, 301, representing the inner VLAN. By separating them into group 1 and group 2, Python allows you to strip away the dots and extract the pure data, integers, out of the raw text string. Thank you very much for watching this video, day 3. Just to recap, we touched on hardened pattern extractions and regex primitives. Hope to see you in the next video. Thank you very much.